Very excited to be here today to present my dissertation research on expert crowdsourcing, which introduces techniques for crowdsourcing complex goals with Flash teams and Flash organizations. So for the next 45 minutes or so, I will show you how we can bring together distributed experts from the crowd within minutes and then enable them to achieve large-scale complex goals such as, should I move over? Can you see okay? Such as software development, video production, and product and game design. Completing goals of this nature used to require traditional teams and organizational structures that were composed of bounded employees or contributors. But over the last decade or so, the emergence of online labor marketplaces has made it possible to quickly bring together paid crowd workers from around the world within minutes to achieve a range of large-scale tasks. And while these online marketplaces have started to change the nature of how work gets done, most of the shifts have been for specific types of goals and crowds. Specifically, crowdsourcing has really focused on goals that can be decomposed into homogeneous microtasks that can then be achieved by pretty much anyone regardless of their expertise. So for example, non-expert crowds recruited from platforms like Amazon Mechanical Turk are often tasked with labeling images and translating text, which are tasks that pretty much anyone can do. The problem with this approach is that it does not easily scale to larger, open-ended, and complex goals, such as the software development and the video production goals that I showed before. When task units are complex and interdependent, you can't really just decompose them into these homogeneous microtasks, especially when they require a certain level of expertise to complete. And so as a result, many real-world goals that require significantly more complexity, expertise, and coordination between workers and requesters remain out of reach for crowds. So to drive crowdsourcing past this complexity boundary, this thesis shifts away from microtask work and introduces expert crowds as a core component of crowdsourcing systems. Expert crowds can be recruited from many different online marketplaces, including Upwork, Freelancer, and 99 Designs. For example, Upwork, which is the focus of this work, allows clients to draw on a contingent global labor pool by providing access to millions of paid experts and professionals with a variety of skills, so including developers, designers, video editors. We've even hired musicians, such as an opera singer. But to achieve complex and interdependent goals, it's not enough to just recruit these experts from Upwork and then assume that just because they have the skills needed to achieve the task, that they will be successful in doing so. Complex work requires coordination among individuals with many different expertise, which in the case of crowd work also requires coordinating interdependent workers who are distributed around the globe and have never worked together before. Easy, right? And so, given these challenges, even though marketplaces like Upwork provide access to experts, most crowdsourcing research has focused on completing tasks with non-expert workers. So as a result, expert crowdsourcing currently lacks generalizable techniques for guiding crowds through complex and interdependent goals. So this thesis proposes that combining expert crowds with computational techniques and organizational structures can fill this gap and enable crowds to achieve complex and interdependent goals quickly, reliably, and at scale. Right, so in this talk, I will present 3 projects which introduce and evaluate 2 techniques for creating team and organizational structures composed of expert crowds. And these approaches are manifested in Foundry, which is a computational platform that we've created for authoring crowd work structures and managing interdependent crowd workers. The first project, Flash Teams, presents a framework for dynamically assembling and computationally managing crowdsourced expert teams. In the second project, I show why the Flash Teams approach, which relies on predefined workflows, won't be sufficient for achieving large-scale and open-ended goals that can't be decomposed in advance. Then, motivated by this limitation, the third project, Flash Organizations, introduces a framework for creating rapidly assembled and reconfigurable organizational structures that are composed of large groups of expert crowd workers. And then, taken together, these projects reimagine a future of work in which teams and organizations are no longer anchored in traditional labor models, but are instead fluidly assembled and reassembled from globally networked labor markets. And the result of this vision is a system that really empowers pretty much anyone with an internet connection to create and lead entire teams and organizations that are composed of paid crowd workers that can achieve complex and open-ended goals. All right, so to give you a sense of the roadmap for my presentation, I will first discuss each of the three projects, and we'll then wrap up with a brief summary of the contributions and the directions for future work. All right, so the first project, which Michael mentioned before, is titled Expert Crowdsourcing with Flash Teams, and we presented this work at WIST in 2014. In this project, we ask, can we use the large pool of expert crowd workers that are available online to carry out complex and interdependent goals? If so, we could take advantage of the scale and flexibility of the crowd, but still take on complex and interdependent work. So for example, could we bring together a team of crowd workers, give them a napkin sketch of an idea, and then have them create a user-tested interactive web app in a single day? How about an animated video in 48 hours? Or better yet, could we bring together multiple teams of crowd workers to create an entire MOOC platform along with content within a day or two? So our objective is to explore the feasibility of solving complex and interdependent goals, such as the ones that I just showed, using structured collaborations between experts from the crowd. As I mentioned before, expert crowd work is independent and uncoordinated, which makes it difficult to use crowds to achieve complex and interdependent goals. But we know from organizational behavior research that even temporary groups can coordinate complex work effectively if they have lightweight team scaffolds. And these scaffolds define who is working together and then who is responsible for which task. And so our goal here is to combine the strengths of team scaffolds with the scale and interactivity of computation to dynamically assemble and manage teams of expert crowd workers. To do this, we introduce Flash Teams, which are computationally guided teams of crowd experts that are supported by lightweight, reproducible, and scalable team structures. Project requesters assemble and manage a Flash team by chaining blocks together to transform a starter input into a desired final output. The complete set of blocks determines which crowd experts need to be recruited and when they're likely to be needed. Then each block is a self-contained, reusable representation that has computational properties. So it requires the skills needed, an input, target duration, instructions, and an output type. So for example, suppose that you're a project requester and you're building a team to execute the user-centered design process, starting from a napkin sketch of an idea that you may have. You might connect the lo-fi mockups from the first block to any other block that takes lo-fi mockups as input, such as a revised mockup block or a heuristic evaluation block. So to put this into context, Here you can see what this Flash Teams complete sequence of blocks and inputs and outputs might look like. All right, so because these Flash Teams are machine readable, we can create entirely new kinds of organizational forms that enable these teams to be replicated, recombined, they can grow and shrink, be optimized, and more. So for example, because Flash Teams benefit from modularity, they can be replicated and used for many different types of projects. Another benefit of modularity is that these teams can be combined almost like Lego blocks to create much larger organizations. Flash Teams also benefit from elastic growth, which enables them to grow and shrink as needed. Flash Teams can be pipelined rather than waiting for the entire task to complete. And this allows computation to automatically optimize these teams. And finally, we can automatically create new teams, ones that may have never even existed before, using the components of previous teams. Okay, so existing project management and microtask management tools really don't capitalize on the scale and affordances of distributed expert crowd work. And so this means that Flash Teams require new kinds of tools and infrastructure. And so as part of this research, we've created Foundry, which is a web platform that is designed to organize, coordinate, and manage distributed expert crowds. Foundry allows project requesters to create Flash Team structures and also allows team members to track their progress and send notifications when handoffs have been issued. With Foundry, requesters can either create a Flash Team from scratch, or they can compose or modify previous team structures from the Foundry Flash Teams library. So to give you a sense of how Foundry works, let's create another user-centered design napkin sketch team. So as a requester, you would first add the team roles by reaching into nearly 2,500 Upwork skill categories. You would then add blocks to the timeline, similar to how you would on a calendar interface, including all of the data around members, inputs, and outputs. You can make dependencies visible by explicitly marking tasks based on their inputs and their outputs. When each block is complete, workers upload their output materials to the Google Drive folder for the project, which Foundry automatically generates. And then if two blocks occur at the same time, so here the hi-fi prototype and the logo design should be working together, you can indicate that these blocks should be in synchronous collaboration. Right, so once you've created your team and you've recruited your workers from Upwork, you would click the Start button on Foundry to enter runtime mode. In runtime mode, Foundry adds a timer to each task in the timeline. And then each worker on your team will receive a unique link that logs them into the Foundry runtime with their tasks highlighted in the timeline. So here you can see that they're all highlighted in yellow, the lo-fi mockups and the revised lo-fi mockups. And then when a worker starts a task, the timer for the task begins. If a task is delayed or it's completed early, Foundry will recalculate the start time for the subsequent tasks, update the timeline, and then notify workers. When a worker marks a block as complete, Foundry notifies workers for the next block that their task is now active. So in order to better understand the design space of Flash Teams and really what they would enable us to do, we recruited experts from Upwork and then ran a series of example projects ranging from design to education. So here you can see screenshots of all of the team deliverables that I'm about to describe. The first series of projects that we ran was with the napkin sketch design team. And we gave 3 different Flash Teams sketches that we took from 3 different Stanford student assignments in the Introduction to HCI class, which I'm sure some people in here have taken, hopefully. And their goal was to produce a fully functional user-tested web prototype. So as shown in the table on the slide here, The completion times ranged from 18 hours to 31 hours and 30 minutes, depending on the amount of pipelining and elasticity. And all of the outputs were fully functional and reflected the original intent. So after completing the napkin sketch design teams, we asked ourselves, can Flash teams support creative outputs and non-engineering domains? To test this, we decided to use a Flash team to create an animated video that was based on a rough script idea, which was to celebrate the retirement of Terry Winograd, which, as many of you here hopefully know, was one of the founders of the Stanford HCI group and a professor in the computer science department here at Stanford for many, many years. And so as shown on the slide, we recruited a director, an animator, sound engineer, script writer, and illustrator, all from Upwork. And then in under 2 days, the Flash team came up with the plot and produced the video, which captured a funny anecdote from Terry's childhood when he built a computer in his garage. So let's have a look at the video that the Flash team produced.
Good morning, son.
Oh, hey, Dad!
What the? What is that?
It's the future! It works!
All right, so the napkin sketch design team and then the animation team that you just saw demonstrated that this Flash team's approach to expert crowdsourcing works. And so our third objective was to combine multiple modular team structures to create a new online learning MOOC platform and to generate 3 short lessons. We added 1 more education Flash team and then replicated and combined the teams to create a much larger organization. For each course, 1 education team created the course content and the quiz materials, and then 1 animation team produced the video. Simultaneously, 3 napkin sketch teams worked on the web platform that was used to upload and share the courses. Taken together, it took the 9 Flash teams 19 hours and 20 minutes to create the MOOC platform and to generate the 3 interactive lessons. And you can see excerpts from each of the 3 courses on the bottom of the slide. All right, so in this project, we had one final question. Does this infrastructure actually help people collaborate? So we conducted a controlled experiment to compare Flash teams to a self-managed teams approach where the experts choose their own path. We collected data with 3 napkin sketch design teams in each condition, totaling 22 crowd experts from Upwork. We asked all of the teams to create a simple party planning task manager from an input sketch. And the main difference between the conditions was the existence of the Flash team's workflow, which defined the sequences of tasks to team members and helped them support coordination via handoffs and notifications. And while all 6 of the teams completed the project, the Flash teams took roughly half as many work hours, which means half the cost. They also followed the iterative design process more closely. They required half as much communication as well as less coordination. And in fact, by active work time, even the slowest Flash team completed the project faster than the fastest team in the control condition. And I explore and discuss some of the qualitative insights from this project in my next project. All right, so to summarize, most crowdsourcing research has focused on coordinating workers that are homogeneous and replaceable. In contrast, Flash teams offer an opportunity to shift the crowdsourcing narrative towards teams of diverse experts from the crowd. All right, so moving on to the second project. The first project demonstrated that computational work structures, such as crowdsourcing workflows, can enable expert crowds to achieve complex and interdependent goals. We noticed, however, that when things went wrong or workers had ideas that they wanted to explore, the Flash teams were constrained by the specifications that were embedded in their workflows. So for example, in the follow-up survey, some of the workers expressed frustration with all of their tasks being pre-planned, which they felt really minimized their need to communicate and coordinate with other workers, and also prevented them from making changes and exploring other ideas. So despite the successes of the Flash teams that I just presented, these challenges point to some potential limitations of crowdsourcing workflows. And so if we hope to achieve our vision for expert crowd work, it's critical that we understand the strengths and limitations of crowdsourcing workflows. Given this objective, in this project we ask, how do crowdsourcing workflows, such as those used by the Flash teams, support and constrain complex crowd work? To answer this question, we conducted in-depth case studies of the 6 teams of crowd workers in the field experiment that we completed in the Flash teams project. For conceptual reasons, we relabeled the Flash teams as workflow-based teams and the self-managed teams as role-based teams. As a reminder, all of the teams were composed of 3 roles, including a UX researcher, a UI designer, and a developer. The key difference between the conditions was that the workflow-based teams enacted pre-specified workflows that decomposed and predefined all tasks and dependencies. In contrast, the role-based teams enacted minimally specified work plans, which were just one long, unstructured task that was assigned to all 3 of the workers. So our analysis here aims to understand how the workflow-based and the role-based teams enacted and adapted their work structures, as well as the challenges that they encountered. The data that informs this analysis includes a mix of chat logs, survey data, observation notes, and other archival data, including all of the Foundry team data, the Upwork work diary data, and all of the task deliverables. To analyze the data, I used an open-ended inductive coding process using NVivo. And during the initial round of coding, I identified common behaviors, practices, and challenges that were encountered in each of the teams. Next, I compared the themes that emerged across the teams and conditions to develop conceptual insights. And as I was doing this, I was constantly going back to the literature on coordination and workflows to further refine the codes. And then once the qualitative analysis was complete, I analyzed the work diary data from Upwork to better understand really what might explain the differences that we were seeing. So in line with prior research on coordination and organizational design, our analysis reveals that neither pre-specified workflows nor minimally specified work plans are fully sufficient for orchestrating complex and interdependent crowd goals. Goals of this nature require coordinating multiple interdependent contributions from diverse workers and adapting work structures and deliverables in response to unplanned contingencies and opportunities that emerge along the way. So this suggests that for crowds to take on complex goals, crowdsourcing workflows really need to support both coordination and adaptation. And at a high level, our results show that crowdsourcing workflows support coordination, but they inhibit adaptation. In contrast, the minimally specified work plans are easier to adapt, but they make coordination more difficult, and they really don't ensure that the best adaptations are the ones that are pursued. So I'll now briefly demonstrate how the workflows supported coordination, and will then show how they inhibit adaptation. The pre-specified workflows encoded best practices in the teams, which helped ensure that the workers didn't make obvious missteps. They also clarified the order and the relationship of the tasks, which reduced the amount of explicit coordination and communication that was needed between the workers. In contrast, the role-based teams had to decide amongst themselves how to proceed, and this often led to inefficient coordination and even incorrect work. All right, so to understand really how the workers enacted their work structures and the extent to which they encoded best practices, we used the Upwork work diary data to reconstruct a timeline of what happened in each of the teams. So the timelines that you see here are grouped by team, and each of the rows represents a role, and then each of the blocks represent a continuous period of time that was logged by the worker in that role. And so what you see here is that all of the workflow-based teams completed the same set of tasks in the same order by workers in the same role. In contrast, the role-based teams all enacted vastly different work plans, and they also adopted much more concurrent work structures. As you can see, these blocks overlap across the rows much more. And so this resulted in workers completing tasks in different orders and at different times, sometimes working simultaneously and other times working independently. And so what this tells us is that by decomposing goals into actionable tasks with clear outputs and constraints, the workflows helped orient and integrate the actions in the team, which led to more consistent and replicable outcomes. And finally, it also became clear that the pre-specified workflows help minimize coordination challenges in the teams. In contrast, the role-based teams encountered many more coordination challenges. So, for example, one of the teams spent 2 hours arguing over their responsibilities, which led to the developer getting fired and then replaced. And then the workers also started to work without first communicating with their team members, and in some cases, they even completed their tasks without notifying dependent team members. So I'll now demonstrate how the workflows inhibited the teams from adapting. It became clear in our analysis that the rigid structure that was imposed by the workflows made it difficult for the teams to respond to contingencies and prevented crowd workers from pivoting when better opportunities emerged. Our results show how the teams responded to different types of contingencies. And here we're defining contingencies as unexpected challenges or occurrences that prevented these work plans from proceeding. In this talk, I will discuss one type of contingency, which was incompatible deliverables. In our data, the incompatible deliverables were caused by workers' deliberate decisions, such as deciding to use a different programming language than the ones that we had explicitly requested, as well as errors and incorrect assumptions. And in almost all of these cases, regardless of how detailed you had made the workflow, these contingencies and incompatible deliverables were difficult to predict a priori. And so given the rigid structure that was imposed by the workflows, the workflow-based teams were unable to respond had trouble adapting when these incompatible deliverables and contingencies occurred. So as a result, workers ultimately just had to accept the deliverables as is and just move on. And since the workflows were unable to detect most of these decisions and assumptions and errors as they were happening, the incompatible deliverables really went unnoticed until the tasks were completed. So, for example, as shown in the chat excerpt here on the slide, one of the UX researchers incorrectly assumed that it would be okay to use his own opinion and judgment when conducting the heuristic evaluation instead of using Nielsen's usability heuristics. And this worker decided to only reveal this assumption to his team members once he had already completed the task. And by that point, the changes that were required were outside the bounds of what the workflows could support, which prevented these teams then from adapting.
Was that person's role as a designer or a usability person?
Yeah, UX researcher.
UX researcher.
And so in contrast, the concurrent and the emergent work structures that were adopted by the role-based teams were able to because of this, the teams were able to catch these missing deliverable details and incompatibilities as they were happening, and therefore before it was too late. So for example, when one of the UI designers finished the mock-ups, the UX researcher quickly reviewed them before conducting the heuristic evaluation. And in this review, the UX researcher noticed that the mockups were missing error messages for incomplete form fields, which then allowed the UI designer to quickly go back and fix the mockups before the UX researcher conducted the heuristic evaluation. In addition to facing contingencies, all of the teams faced situations in which their work structures or plans really weren't best suited for their local context or their current situation. And when these mismatches occurred, the role-based teams could adapt their work plans, whereas the workflow-based teams were bound to the specifications that were embedded in their workflows. So for example, in an attempt to minimize delays that were caused by the UI designer not showing up, the developer in one of the workflow teams wanted to work in parallel, but was ultimately unable to revise the work structure and just had to wait. In contrast, the role-based teams would internally establish informal deadlines and then adapt them as needed. So for example, when time was running out, the teams adapted their work structures by prioritizing the key tasks and then collaborating to make sure that they got done. The crowd workers also attempted to improve their mobile web apps by pursuing alternative opportunities, such as adding new features that they felt were important. The workflow-based teams, however, were limited by the predefined work structures and the constraints that were embedded in these workflows. And so as a result, all of their attempts to add new features, such as their attempts to add search, delete, pagination, and sort features, were all unsuccessful. In contrast, while the role-based teams attempted to add fewer features, they were much more successful when doing so. So to conclude, this project sheds light on some of the reasons why crowds struggle with complex work. Our findings suggest that while crowdsourcing workflows are important coordination artifacts, they stymie the crowd workers' ability to adapt in response to unplanned contingencies or opportunities that might emerge. And given that it is impossible to predict all possible contingencies and adaptations, crowdsourcing workflows are, in their current form at least, are fundamentally incompatible with complex goals. So taken together, these results suggest that there's really no such thing as a perfect workflow for complex crowd work. Crowdsourcing workflows need to take into account both the attributes and the uncertainty of the task and the environment, which few workflows currently do. And finally, these results also surface an interesting workflow paradox. So by preventing bad outcomes, such as coordination challenges, our results show that workflows and these formal coordination structures are also preventing good outcomes and desirable adaptations. All right, so moving on to the third and final project. So as we saw in the first project, the Flash teams demonstrated that we can crowdsource complex and interdependent goals. But as we saw in the last project, the pre-specified workflows that were used by the Flash teams struggle to scale to goals that can't be defined in advance. And so motivated by this insight, in this last project, we asked whether we can crowdsource goals that are complex and evolving. And by evolving, we're referring to goals that are loosely defined and can't be decomposed in advance. Goals that are loosely defined and evolving are not easily adapted for crowdsourcing. Unlike goals that are completed by microtask workers and the Flash teams, open-ended goals such as invention, production, engineering are all difficult to articulate, modularize, and pre-specify all of the possible actions that are needed to achieve them. In contrast, traditional organizations regularly orchestrate large groups in pursuit of very open-ended goals. So unlike existing crowdsourcing infrastructures, organizations coordinate work by arranging employees into a set of formal organizational structures such as roles, teams, and hierarchies. And these structures encode responsibilities, interdependencies, and information flow, but they do not necessarily articulate and pre-specify all of the sequences of actions that are needed to achieve them. So in order to achieve similarly open-ended goals with crowds, we explore an alternative crowdsourcing approach that combines organizational structures with computational crowdsourcing techniques to create flash organizations. Flash organizations are rapidly assembled and reconfigurable organizational structures that are composed of large groups of online crowd workers. To achieve complex and open-ended goals, Flash organizations computationally instantiate roles, teams, and hierarchies. They populate these structures on demand by issuing open calls to experts in paid crowdsourcing marketplaces such as Upwork. And the Flash organizations can then reconfigure these structures to responsively adapt the organization's activity, which enables orchestrated efforts towards open-ended goals. All right, so here's an example of a Flash organization structure. The organization is composed of many different roles, which are nested into teams, which are then nested under the organization's leader. And as I'm about to show you, the roles, teams, and hierarchy that make up the Flash organization structure are computationally instantiated, populated, and reconfigured using Foundry, which you had seen before. So Foundry represents a Flash organization as a set of hierarchically nested roles, which it then uses for open call hiring from the crowd. And it also uses it to execute the tasks, as you'll see in a second. And each role indicates a position for a crowd worker, specifies the expertise needed to fill the position, and then assigns the role a level in the organization's hierarchy. Foundry populates the organizational structures using automated on-demand hiring. And the way that this works is that when a user adds a new task to the timeline, Foundry immediately begins the hiring process for the necessary positions to complete that task. And so Foundry initiates the hiring process by emailing qualified workers to notify them that a new position that requires their skills is available on a first-come, first-served basis. The first worker to click on the link in the email has 10 minutes to read the details of the task and then choose whether to accept it and start working. And others remain in the queue in case that first worker declines. The organization and the team leaders also have the option to manually hire specific workers and then assign them to a role. When a worker accepts a task, Foundry launches an interactive onboarding tour that provides them with a description of the organization's goals as well as their individual tasks. And then Foundry enables reconfiguration of organizational structures using a branch and merge technique that is inspired by distributed version control. And this technique essentially decouples the current state of the code from any proposed edits. And then Foundry adapts this model to enact both top-down organizational changes as well as bottom-up changes that are driven by the workers. And any member of the organization can branch the current organizational structure, make any desired edits, and then issue a pull request for review by one of the organization's leaders, who can then decide whether to merge it into the ongoing organization. All right, so here you can see two screenshots of how Foundry displays changes in a pull request. The left screenshot shows the current organizational structure, and then the right screenshot shows the proposed change requests, which in this case shows a task that was added in orange and then a task that was erased in white. And any organizational structure within Foundry can be edited. This includes changes to roles, teams, the hierarchy, and tasks. Okay, so to evaluate whether Flash organizations can in fact achieve large-scale and open-ended goals, we conducted 3 proof-of-concept experiments. We recruited 3 leaders from outside of our research team, gave them a budget, and then allowed them to create and lead a Flash organization using Foundry over the course of 6 weeks. All of the workers were recruited from Upwork. And the 3 organizations, each of which I'll show you in a moment, spanned across software, product, and game design. The first organization, EMS Trauma Report, was designed and led by a medical resident. And this organization used the crowd to create a functional prototype of an Android mobile and web application that allowed EMS workers to report a trauma injury from an ambulance on their way to the hospital. The web application also supported accessing and managing the trauma cases. So here you can see some of the screenshots from the mobile web app, or the mobile app and the web app, as well as a marketing video that the crowd had produced. The second organization, True Story, was designed and led by a team of crowd-funded card game makers. And this organization used the crowd to design, manufacture, and playtest a storytelling card game, as well as an accompanying mobile and web application. The crowd designed and produced 2 80-card decks with story prompts, as well as an app for recording the stories and a web app for downloading and sharing the story recordings. And finally, the third organization, Enterprise Workshop Planning Portal, was designed and led by an employee of an advanced technology labs group within a large software consulting group. And this organization used the crowd to create an enterprise IT portal to administer client workshops. So here are the final organizational structures for the 3 organizations. In total, the organizations collectively comprise 93 crowd workers, including 22 team leads and 24 teams. EMS Trauma Report, the first organization there, had the most diverse team structures and was the most complex out of the organizations. True Story was the flattest organization, meaning that it had the fewest team leads. And the Enterprise Portal organization had the fewest teams, and the teams were relatively large compared to the other organizations. Hopefully everyone can see. And so taken together, the 93 crowd workers completed 639 tasks across a total of 3,261 person hours of work time. The median task across the organizations lasted a little bit over 3 hours, and all of the organizations completed the work within 46 days. The organization and team leads utilized Foundry's automated hiring functionality to fill 75 new roles in the organization structure using Upwork. And so as you can see here are the hiring times for each of the 3 organizations. And across all 3 of them, the median hiring time was 13 minutes and 40 seconds, which is extremely fast. In contrast, manual hiring from the Upwork marketplace required a median of nearly 15 hours. And in total, the organizations filled 20 roles with manual hires. And just for context, traditional organizations take between 14 and 25 days to hire, which is obviously much longer. And so during each of the projects, the organizations continuously adapted to, Yeah.
The manual hiring. Was there a way to check the quality of hiring?
Yeah, so I didn't go into this in detail, but we created these panels. Should I answer questions now, by the way? Is there more? So we created panels for the different roles that we thought would be needed, and we interviewed and gave them starter tasks in advance in order to join that panel. And then once they were on the panel, any task that required the skills that had been screened for on the panel was then used. So that's where we sent the emails to. So panels were associated with roles. Does that answer your question?
Yeah, I'm just thinking like further down the road, let's say if you try to take like a month of work of someone who was hired by automated hiring versus manual hiring, was he like a better employee, not as like maybe something like that?
Yes, so the manual hires tended to be more for like team leads or for people who had like specific skills where you really wanted to screen, and we can talk more about it later. But I think that would be an interesting analysis to run for sure. So during each of the projects, the organizations were continuously adapted to the changing conditions by adding and revising people, tasks, teams, and time. And in total, the organization submitted 566 pull request changes with an average of 4.5 pull requests per day per organization. And while the breakdown of requests by source varied across the organizations, on average, 22.4% of the requests came from the workers, 68.2% came from the team leads, and 9% came from the organization's leaders. So as you can see, the changes here to the organizational structure were both top-down per the leader's directive and then bottom-up per the workers' initiative. So here you can see in this very large table a summary of the outcomes that I just described. So as these results demonstrate, all three of the organizations successfully achieved their goals. And furthermore, all three of the final deliverables passed a quality review from different neutral expert reviewers that we had found to review these applications. And in terms of cost, the cheapest organization was True Story, which came out to $6,650. And the most expensive organization was EMS Trauma Report, which came out to $46,190, which is much more. So to wrap this up, in this paper we demonstrated a technique that combines computational organizational structures with the on-demand networked global workforce to produce organizations that can grow, shrink, and rearrange themselves in real time. Flash organizations advance a future of work that is increasingly mediated by computation and algorithms and open a set of goals that up until now have really been out of reach to crowdsourcing. Okay, so I'd now like to wrap up with a brief summary and discussion of the contributions as well as the directions for future work. So to summarize, this thesis shifts away from crowd work that relies on homogeneous microtask workers. Instead, we introduce interdependent teams and reconfigurable organizations that are composed of expert crowd workers. Specifically, we present 3 projects which combine literature, theories, and methods from organizational behavior, human-computer interaction, and computer science. And through these 3 projects and this interdisciplinary approach, we introduced and evaluated a novel combination of expert crowds, organizational structures, and computational techniques for completing highly complex and interdependent goals which have been out of reach to crowds. Collectively, these 3 projects help inform the design and the general understanding of crowdsourcing techniques and computational systems at both the team and the organization level. And more broadly, this research makes contributions to crowd computing, system design, and organizational design. First, this thesis introduces expert crowds as a core component of crowdsourcing systems. And specifically, Flash teams and Flash organizations contribute 2 computational approaches for coordinating expert crowd work. And these approaches expand the capabilities of paid crowd work and crowd computing by enabling complex and open-ended goals. Second, our computational platform Foundry contributes a new crowdsourcing system that's capable of authoring and orchestrating a range of complex crowdsourced goals. So to our knowledge, Foundry represents the first computational authoring and coordination platform for interdependent expert crowd work. And furthermore, the insights from the Flash team and the Flash organization's deployments, both of which used Foundry, contribute to the design space as well as our understanding of computational crowdsourcing systems and techniques. Finally, this thesis also advances research on organizational design. Flash teams and Flash organizations represent the first examples of computational systems and frameworks that encode and reconfigure temporary role-based coordination structures that are capable of achieving complex and interdependent efforts online. And so this thesis really envisions a world in which work can occur online by experts who have never worked together before. Flash teams and organizations serve as initial examples of this vision, but they also open up several interesting opportunities for future work. First, given that most complex goals can't be completely pre-specified in advance, and that it's pretty much impossible to predict all of the possible contingencies that might occur along the way. Future work really needs to explore approaches for supporting flexible work structures and emergent coordination while making sure to maintain the scale and affordances of computation. Second, most existing marketplaces really were not designed around interdependent expert crowd work. And as a result, they have critical limitations, including hiring transaction costs and search frictions. Similarly, most existing coordination tools such as Asana, Skype, Basecamp, and Slack, which I'm sure many people in this room, including myself, use, were not designed to integrate with crowdsourcing marketplaces, and were definitely not designed to support short-term yet complex crowd work. So while platforms like Foundry begin to fill this gap, there's really a big opportunity for researchers to design new types of marketplaces and coordination tools that are centered around interdependent and on-demand expert crowd work. Finally, Flash teams and organizations suggest important research directions for traditional teams and organizations. So, for example, many large or distributed organizations could view their own employees as a crowd and then convene them using these computational techniques on demand. Flash teams and organizations also introduce the opportunity for new types of hybrid teams and organizations that are composed of both internal crowds like their employees and external crowds from these marketplaces. And so, for example, you could imagine a startup supplementing their founding team with additional expertise from the crowd as the needs of the organization evolve. Or you could imagine a large organization supplementing their project teams with expertise that they don't currently have available internally. All right, so I'd quickly like to wrap up with some thank yous. I would first like to thank all of the organizations that have funded this work, especially the Stanford Interdisciplinary Graduate Fellowship. I'd also like to thank all of my amazing collaborators that have contributed to this work. It really would not have been possible without this incredible team. I would like to, of course, thank all of the Upwork workers who participated in this research, because we learned a ton from them, and we hope that this work ultimately builds a brighter future of work and opens new opportunities for them. Next, I'd like to acknowledge and thank the WTO, MSNE, and HCI research communities, as well as the staff for their support and their friendship over the last 5 years. And most importantly, I'd like to thank my advisors and my committee, Michael, Melissa, and Pam, for their ongoing support, feedback, and guidance. At times, I really wasn't the easiest student to advise, given my interdisciplinary interests, as Michael mentioned before. But the three of them really worked together to support me along the way. And so thanks to the three of you, I was really able to achieve my goal of conducting research across organizational behavior and HCI. So I'm really appreciative for everything that you've taught me and everything you helped me achieve. I'd also like to thank Jeff Hancock and James for taking the time to be here and for agreeing to be on my examining committee. And finally, I'd like to thank my fiance, Andrew, who's here today, for his unconditional love and encouragement and for listening to countless practice talks. And finally, I want to thank my parents and my sister, who couldn't be here today, for all of their love and their support and patience over the last 27 years. So that's all that I have, and I'm now happy to take questions.
So we have time for a few questions from the audience, and then we'll convene in the closed session.
Yeah, I found this absolutely fascinating because I've spent tens of thousands of dollars on Upwork and hired like 40 to 50 freelancers from Upwork. So I was wondering if you're gonna plan to take Foundry to market, like try to make it a startup, yeah, like.
So that's a great question, and we get it a lot. So right now we are working on developing it for more of like a public launch, not necessarily a startup, but we get emails a lot from researchers and from some companies that want to use it. And so we are trying to make it transfer it from a research platform that we designed for ourselves to a tool that other people can use. And we'll send out an email to the group when that is done. We're hoping for V1-ish by the end of the quarter, so we'll keep you posted. You're welcome.
This is super cool, especially the bits at the end about sort of self-adaptation and whatnot. Sort of random question, if you had like a ton of money and you could throw some kind of machine learning at this problem, some part of the adaptation stuff, like any part of the sort of last bit of the system you're talking about, what do you imagine you would do with it, or what would be some creative ways to even start thinking about how you combine stuff like that?
Yeah, so it's a good question. We've actually thought a lot about it as we think about the next steps for this, and I think one of the most interesting areas in that space is automatically generating these workflows and helping them adapt along the way. So one idea that I had the other day was you could imagine having something like Waze, which adapts your directions as you go based on crowdsourced data. And so you could imagine having something like that for these workflows where it would kind of suggest different tasks based on what's happening. If a task is delayed, or maybe you need additional work, or you could imagine there being different paths after each task that it could then suggest. And if that doesn't work, as we saw, you can't be too constrained, then you could kind of come up with your own path. But I think that helping people kind of guide the workers and create these workflows is a big area for machine learning. But to do that, we would need not even as much money, but we would need data. And so we would need to run a lot of these to really understand what should happen.
How do you manage institutional knowledge? So, for example, in a software project, when you go from V1 to V2, you might have completely different teams that pop up as a result. So how do you avoid having the same mistakes that might have been inefficient in V1 and V2?
Yeah, so that's a good question. And I think right now, that's probably one of the limitations of this approach. If you're trying to build a very long-term project that has a lot of embedded institutional knowledge, you would probably want people who are around for the whole time. Whereas this approach is better for something with more of a start and an end point. But having said that, we built some stuff into Foundry to help encode some of that knowledge. So each of the tasks have documentation questions that workers need to answer along the way in order to complete their task. And then when a new worker comes in, part of that onboarding process that I showed is that they have to review that documentation. And then we also integrate Foundry, which I didn't show, with Slack. And so all of that data and all of that information is also there. But you could imagine, making these systems smarter and showing that knowledge in different ways. But it's a good question and obviously a limitation.
Are you able to encapsulate sort of groups within the full set so that they might be reusable? In other words, you're sort of creating components of parts that might be reused again in a future task?
Yeah, so I have two responses to that. One is that I think the marketplaces themselves could almost do a better job of creating these teams and showing you which people have worked together so that you could almost hire them together. And Nilafar, who's here, is doing some work on that. Is Nilafar here? No, it's here. But yeah, there are students who are working on that idea. And then the other thing is that I didn't show it here, but a lot of the workers were rehired. So if a requester or a team lead had a good experience with a worker, they would just rehire them for the next task. So you don't always have to hire new workers for tasks. You can take people that you've worked with before. And I think over time you could imagine optimizing this on-demand hiring process to take that into account.
One more question?
Gonzalo.
So can you explain how the theory of team scaffold is enacted by Clash teams and implemented in Foundry?
Yeah.
And also is also enacted in the team organizations? Do you still use the theory of team scaffold in Flash organizations?
Yeah, so team scaffolds, which is Melissa's research, she's on my committee, essentially showed that these role-based team structures could be just by having roles on a team that can be it will help these teams coordinate because the workers themselves don't actually need to have as much experience, let's say, working together, but because they have experience with that role, those roles help define their responsibilities, and that allows them to then work together. And so we took that with Flash Teams, and we said, well, we have all these crowd workers that are available online, and we know, generally what the roles that are needed to complete these goals are. So it didn't matter like exactly which worker filled that role as long as that they had the skills. And so that's kind of how we took inspiration from Team Scaffolds into Flash Teams. And then in Foundry, as you saw, you add the roles, and then you also add, I don't know if it was in the screenshot that I showed, but you also add the skills that are needed for that role. And so that helps then define the kind of the requirements for that person, and those roles are then assigned to the tasks that they're responsible for, which kind of defines their responsibilities. And even if they haven't worked together before, they know what their requirements are, and they know kind of what the responsibilities of the rest of their team is. And then this definitely transferred over to the Flash organizations. And so there we were trying to coordinate much larger goals of people who had never worked together before. And so there's this term of asset specificity where workers over time develop established like collaboration patterns, and they can become much more efficient, which is, I guess, getting to your question before. And so there the roles also help with that challenge. So it definitely was a big part of all of this work.
We'll take one more question. Any more questions offline, and then reconvene into the closed session. Thank you.
Out of reach for crowds. So to drive crowdsourcing past this complexity boundary, this thesis shifts away from microtask work and introduces expert crowds as a core component of crowdsourcing systems. Expert crowds can be recruited from many different online marketplaces, including Upwork, Freelancer, and 99 Designs. For example, Upwork, which is the focus of this work, allows clients to draw on a contingent global labor pool by providing access to millions of paid experts and professionals with a variety of skills, so including developers, designers, video editors. We've even hired musicians, such as an opera singer. But to achieve complex and interdependent goals, it's not enough to just recruit these experts from Upwork and then assume that just because they have the skills needed to achieve the task, that they will be successful in doing so. Complex work requires coordination among individuals with many different expertise, which in the case of crowd work also requires coordinating interdependent workers who are distributed around the globe and have never worked together before. Easy, right? And so, given these challenges, even though marketplaces like Upwork provide access to experts, most crowdsourcing research has focused on completing tasks with non-expert workers. So as a result, expert crowdsourcing currently lacks generalizable techniques for guiding crowds through complex and interdependent goals. So this thesis proposes that combining expert crowds with computational techniques and organizational structures can fill this gap and enable crowds to achieve complex and interdependent goals quickly, reliably, and at scale. Right, so in this talk, I will present 3 projects which introduce and evaluate 2 techniques for creating team and organizational structures composed of expert crowds. And these approaches are manifested in Foundry, which is a computational platform that we've created for authoring crowd work structures and managing interdependent crowd workers. The first project, Flash Teams, presents a framework for dynamically assembling and computing. And while these online marketplaces have started to change the nature of how work gets done, most of the shifts have been for specific types of goals and crowds. Specifically, crowdsourcing has really focused on goals that can be decomposed into homogeneous microtasks that can then be achieved by pretty much anyone regardless of their expertise. So for example, non-expert crowds recruited from platforms like Amazon Mechanical Turk are often tasked with labeling images and translating text, which are tasks that pretty much anyone can do. The problem with this approach is that it does not easily scale to larger, open-ended, and complex goals, such as the software development and the video production goals that I showed before. When task units are complex and interdependent, you can't really just decompose them into these homogeneous microtasks, especially when they require a certain level of expertise to complete. And so as a result, many real-world goals that require significantly more complexity, expertise, and coordination between workers and requesters reputationally managing crowdsourced expert teams. In the second project, I show why the Flash Teams approach, which relies on predefined workflows, won't be sufficient for achieving large-scale and open-ended goals that can't be decomposed in advance. And then motivated by this limitation, the third project, Flash Organizations, introduces a framework for creating rapidly assembled and reconfigurable organizational structures that are composed of large groups of expert crowd workers. And then taken together, these projects reimagine a future of work in which teams and organizations are no longer anchored in traditional labor models, but are instead fluidly assembled and reassembled from globally networked labor markets. And the result of this vision is a system that really empowers pretty much anyone with an internet connection to create and lead entire teams and organizations that are composed of paid crowd workers that can achieve complex and open-ended goals. All right, so to give you a sense of the roadmap for my presentation, I will first discuss each of the three projects, and will then wrap. Very excited to be here today to present my dissertation research on expert crowdsourcing, which introduces techniques for crowdsourcing complex goals with Flash teams and Flash organizations. So for the next 45 minutes or so, I will show you how we can bring together distributed experts from the crowd within minutes, and then enable them to achieve large-scale complex goals such as, should I move over? Can you see okay? Such as software development, video production, and product and game design. Completing goals of this nature used to require traditional teams and organizational structures that were composed of bounded employees or contributors. But over the last decade or so, the emergence of online labor marketplaces has made it possible to quickly bring together paid crowd workers from around the world within minutes to achieve a range of large-scale tasks.